Hey everyone. We're going to talk in this video about a topic that we've sort of seen on the edges of this course, but never really talked about explicitly. It's graphing of energies. Now, why might we be interested in graphing energies? Well, the reason is that it's sometimes just easier to convey information with a graph. A graph can allow us to see exactly how each kind of energy changes during a process. Graphing is, at the end of the day, just another way of representing the same kinds of information that we've been representing mathematically. But it turns out that having graphs of your energies allows you to determine other things about the way that the system will behave that we just can't determine directly from the math, at least with what we know. So in this video, we're going to spend some time graphing some energies. So let's do that. Let's go to the whiteboard and learn a little bit about how we can graph energies. Here's a practice problem for graphing energies. Now, this practice problem is actually one of the practice problems that I've uploaded to Canvas for your midterm practice. So this is a really good example of the kind of thing you would expect to see on an exam with this kind of problem. Let's read it together. A 10-kilogram meteorite enters Earth's atmosphere. At an altitude of 1,000 meters, it is traveling at the speed of 200 meters per second. In the next 300 meters, it starts to heat up, i.e., assume initial thermal energy to be zero, due to friction, and its speed falls linearly with height until it reaches a terminal speed of 100 meters per second, constant speed at 700 meters above the ground. It remains traveling at that speed until it hits the ground. Assume the meteorite does not evaporate. Plot all the energies involved in kilojoules, including the total energy below as a function of height from just before the meteorite hits the Earth to 1,000 meters in the air. Don't forget to label the axes. So let's do that. Now, the first step whenever you're trying to graph a problem is to try to figure out a place where you actually know what the energies are equal to. Doing this will allow you to place points on the graph that you can eventually connect together with lines. Let's start at the beginning of this problem. It tells us that at an altitude of 1,000 meters, the meteorite is traveling at a speed of 200 meters per second. From this information, we can calculate actually two things. We can calculate the gravitational potential energy of the meteorite and the kinetic energy of the meteorite. So let's do that. We know the mass of the meteorite is 10 kilograms. It's given to us right at the beginning of the problem. So all that we have to do is just plug our numbers into the kinetic and potential energy equations to get an answer. Now, I haven't done anything fancy here. I've just taken the numbers that were given and plugged them into the equations that we have for energy. We end up with 100,000 joules for the potential energy at the beginning of the problem, and we end with a kinetic energy of 200,000 joules. In this problem, we're being asked to graph in kilojoules. A kilojoule is just 1,000 joules, so 200,000 joules is just 200 kilojoules. Let's mark these energies on our plot. Now, when we're plotting energies, energy will always be measured on the vertical axis, whereas the position will be measured on the horizontal axis. Let's start by marking our potential energy. At a height of 1,000 meters, the potential energy is just 100 kilojoules. The kinetic energy at the height of 1,000 meters is just 200 kilojoules. The only other kind of energy in the problem is thermal energy, and we're actually told explicitly what the thermal energy is at the beginning of the problem. It's right here. Assume initial thermal energy to be zero. So let's mark thermal energy on our plot. If we know the total energy at any one point in time, we know the total energy at all points in time. It's going to be the same as long as the system is closed. We're going to say that this is a closed system, and we've already calculated what all the different energies are at some point in time. at the point when the asteroid hits the atmosphere 1,000 meters above. So let's just compute what the total energy is by adding all those up. We can immediately draw our graph for total energy. Total energy is not changing during this process, so its graph is just a straight horizontal line. This is great, but it's not much of a graph yet. Let's see if there's another spot in the process where we know something about the energies. The problem says, in the next 300 meters it starts to heat up due to friction, and its speed falls linearly with height until it reaches a terminal speed of 100 meters per second, constant speed at 700 meters above the ground. The asteroid is being slowed down by its contact with the air, and we're given exactly how fast it's going at that particular height. So we can do the exact same thing that we did before. We can calculate the gravitational potential energy at 700 meters per second, and we can calculate the kinetic energy because we're given the speed at 700 meters per second. I trust that by this point in this course, you're capable of plugging in numbers to the kinetic and gravitational potential energy equations. So I'm not going to write this out, I'm just going to write down the answers. I calculate that when the asteroid has reached 700 meters above the ground, it has a kinetic energy of 50 kilojoules and a potential energy of 70 kilojoules. So let's mark those on our plot. We've already determined what the total energy for the system is for the entire time. That total energy is made up of three other energies: the kinetic energy, the gravitational potential energy, and the thermal energy. Our kinetic energy plus our potential energy at this point is equal to just 50 plus 70, 120 kilojoules. If the total energy is 300 kilojoules, that immediately tells us that the thermal energy must be equal to 180 kilojoules. But what is the shape that should be connecting these points? Let's start with the potential energy. The potential energy is the easiest here because gravitational potential energy is related directly to height. All that means in this case is that if the height is cut in half, the gravitational potential energy is cut in half. So graphing gravitational potential energy as a function of height is just a straight line. Now what about the kinetic energy? Well, the problem tells us up here that the speed of the asteroid decreases linearly with height until it reaches a terminal speed of 100 meters per second. But does this mean that our graph for kinetic energy is also a straight line? The answer turns out to be no. The reason is that kinetic energy doesn't depend directly on the speed. It's the speed squared that matters. So even though the speed is decreasing at a constant rate, the speed squared does not decrease at a constant rate. Because this is squared, it looks like a parabola. Now, it is not the case that graphs of kinetic energy will always look like parabolas. Speed doesn't appear on this graph, only height and energy does. So a graph of kinetic energy like this will not necessarily be a parabola. Now, this stuff is a little bit tricky, so if you struggle with it, I encourage you to bring it to office hours. But what about the thermal energy? We know the total energy of the system, and we know how the other two kinds of energy that the system has are changing as the object falls. So our graph of thermal energy just needs to be drawn so that the total energy of the system is always the same. At this point, we're mostly doing pattern matching. Mostly you need to demonstrate that you understand how the energy is changing. As long as it looks approximately right, in other words, as long as all the energies in your system approximately add up to the total energy, you're going to be fine. Alright, the hard part of this problem is actually over. Now we just need to know what the asteroid does as it falls the rest of the way to the ground. Let's start with the kinetic energy. We're told that it reaches its terminal velocity at 700 meters. It remains traveling at that speed until it hits the ground. So, for the rest of the time that it's falling, the asteroid's speed is not changing at all. and so its kinetic energy is not changing. So the graph of kinetic energy between 700 meters and 0 is just a straight horizontal line. There are no changes. What about gravitational potential energy? Well, what is the gravitational potential energy of an object at 0 height? Well, it's just 0, right? We know what the gravitational potential energy is when the object hits the ground. What about the line connecting the two gravitational potential energy points? Well, it probably doesn't surprise you that it's still just a straight line. We're still graphing gravitational potential energy with respect to height. Gravitational potential energy depends directly on height. So we know that this gravitational potential energy line just continues until it reaches 0. The last thing we have to think about is the thermal energy. Let's see if we can figure out what the thermal energy of the asteroid is when it hits the ground. We do this the exact same way we calculated thermal energy before. We know the total energy, and we know what the gravitational potential energy and the kinetic energy are equal to when the asteroid hits the ground. The gravitational potential energy is 0. The kinetic energy is just 50 kilojoules. It hasn't changed. So the thermal energy must be equal to 250 kilojoules, so that the total energy of the system is 300 kilojoules. But what is the shape of the line connecting these 2 points? Well, the kinetic energy is not changing during this time. It's just a flat horizontal line, so it's not going to have an effect on the shape of the thermal energy line. The only other kind of energy that's changing is the gravitational potential energy, and it's decreasing linearly, just in a straight, slanted line. And so, because all of that energy is being transferred into the thermal energy of the asteroid, the thermal energy just does the exact opposite. It just increases linearly until it reaches its maximum. And there we have it, our first completed energy graph. It's a nice little way of encapsulating a bunch of information in a relatively small space. Now, as I said, these graphing problems can be a bit challenging. There are several practice problems that cover this exact thing. I encourage you to work on them. And if you're struggling, I also encourage you to bring this to office hours. We're always happy to help. That's all for this video. I'll see you in the next one.